chord, okay? A, let's call this point P, and this is B. So A and B are on the circle, okay? P is not on the circle, P is interior. All right, the distance from the center of a circle to a chord, so that means this distance here, this distance here from the center of the circle to the chord is the measure of the perpendicular segment from the center to the chord. From here to here is the same thing as a perpendicular segment from here to here. It's another way of saying that the shortest way from the center to a chord is by drawing a right angle to it. All right? This little box means that this is 90 degrees, a right angle. It's perpendicular. All right. This opens up some other things that you need to know. If a radius is perpendicular to a chord, then it bisects the chord. So let's go ahead and extend this and make it a full-on radius. And let's call this point here x. So OX is a radius, right? Well, look, if it's perpendicular to this chord AB, then it bisects the chord. So now this segment here and this segment here are equal to each other. They're equal lengths, and they're congruent to each other. All right? Okay, then you can look at it the other way. If this is equal to this, then this is perpendicular to it. Okay? So another way of saying that is, if a radius of a circle bisects a chord, then it is perpendicular. So this bisects it, then it's perpendicular. Or if you know it's perpendicular, then you know it bisects it. So you have that relationship between perpendicularity and bisecting. Anytime you see a chord and a line coming out from the center, anytime. Okay, and then one third theorem that we get from this is that the perpendicular bisector of a chord passes through the center. So let's say that we know that xp from here to here, we know that it's the perpendicular bisector of AB. So in other words, we know that it's perpendicular, and we know that it bisects it into two equal parts. Well, therefore, we also know that if you extend xp, it must go through the center at some point. Okay, so let's start opening this up to some questions. A lot of these questions involve shapes that are overlying a circle. So you might see a circle with a triangle lying on top of it, right? Or a circle with a radius and some chords, and the radius is passing through that chord. So all of these are the kinds of problems that you need this information to solve. Let's give it a try. Lock you back in. So again, you'll notice I'm not using any kind of stencil. You don't need it. So let's say that you're given a drawing, okay, a diagram. And it's got a circle in it. All right. We'll call this circle Q for now. And there's a point on the exterior of the circle. Call that P. And then you got a chord back here. S, T. So this point is T here. This point is S. All right. And then those connect to make a triangle. You notice how fast I'm making this drawing. Okay. You don't need rulers. And then this little bit here, this point here, we'll call R. Q is on this line, all right? So you're given circle Q. Given circle Q. That means you know that Q to any of these points is a radius. Okay? QS is a radius, QT is a radius. And you know that PR is perpendicular to ST. Well, here's PR and here's ST. So let's make our little perpendicular lines, okay? Prove that PS is congruent to PT. So we need to prove that this piece here is congruent to this piece here. So how do we do that proof? Okay, well, you know how to set up your two-column proofs, right? So number one, on the left side, you write your givens. Circle Q and PR is perpendicular to ST. And on the right column, you write given. All right, number two, PR bisects ST. Let's see, PR bisects ST. How do we know that? Well, remember what I just said. If a radius is perpendicular to a chord, here's a radius. Oh, you might say it's not a radius, it doesn't go all the way through. Make it go all the way through, right? All lines theoretically go on forever, so you can just extend it to this unnamed point right here. See that point? So now we know that QR is a radius. And we'll call that special point, we'll call it XX, just for kicks. So if this radius is perpendicular to this chord, and it is, because that's given, then it bisects the chord, right? QR is part of a radius. If it bisects it, let's go ahead and write on our diagram these congruency lines. So now we know that SR is congruent to TR. You know where this is going? I think you know where this is going. Okay, so PR is the perpendicular bisector of ST. This is your third step. On your left column, you write PR, right, is the perpendicular bisector of ST. That's just for your reason, you just write, it's a combination of steps 1 and 2. Your teacher might not even make you say that. You know that QR, right, is perpendicular to ST and it bisects it. So PR, which is on the same line, this confuses a lot of people. Lines are just whatever. You make lines whatever you want them to be. Don't overthink a line, okay? PR is the perpendicular bisector to ST. Okay, finally, your fourth step is the answer to the proof. You're trying to prove that PS is congruent to PT, and that's the claim you make. PS is congruent to PT. And your answer is, if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints. So let's see here. Do you have a point on the perpendicular bisector of a segment? Well, here it is. This point is on the perpendicular bisector, right? P. You had another point way out here, and hey, why not let's make one, right? And let's call that point question mark. That's still on the perpendicular bisector. Any point on this line counts as being on the perpendicular bisector of this segment. And you know, this is from a previous theorem, if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints. That might confuse you. But then I want you to think to your triangles, right? Remember side, angle, side? So they have one side that's shared, this side. So in that way, these two triangles have one side that's congruent, the shared side. Another side, which is here, right? And an angle in between those two sides, the right angle. So we have side, angle, side. So we have the two triangles are congruent. So that's another way you could do it, where you can find that then these far sides, the hypotenuses of the triangles, are also congruent. In this case, though, we're using the reason if a point is on the perpendicular bisector of a segment, like that one, or that one, or that one, then it is equidistant from the endpoints. What else can we draw from this? See point double X, right? It's on the perpendicular bisector, so we know that this line is congruent to this line. What about the center of the circle, Q? Yep, we know that this line is congruent to this line. See? It's like a kite. I don't know if you've done kites yet. All right, let's look at another problem. Another problem.